And it turns out that the closure problem does not depend on omega and so forth. So this is the same model I have presented before. Now it's a little bit more involved for the non-equilibrium model. So I have the same closure plus an additional stuff here that will be used to distribute the heterogeneous source between the two macroscale equations. So the macroscale equation, they look like the same as before, plus the average of homogeneous sources, same case. And then omega is distributed between the two equations with a distribution coefficient that essentially depends on the closure problems associated with this mapping scalar. That's the main feature of the system, and I just want to finish that. So there is a problem for this distribution coefficient. I won't go into many details. So let us look at this this distribution coefficient. Well, it looks like that. If I take, for instance, a stratified system and I change the Fermat conductivity ratio, it looks something like that. If K sigma over K beta goes to infinity, the distribution coefficient goes to 0. And the distribution coefficient, in my definition, where is the equation? It's here. If C is equal to 1, everything goes in the beta phase. And if C is equal to 0, everything goes in the sigma phase. This is just a definition. So if K sigma over K beta tends to infinity, C is equal to 0, all the heat is in the sigma phase. Well, that's the engineering practice. So if you are in this situation, the engineering practice is okay. And it turns out that most of the applications are with metals. So a huge difference between K sigma and K beta. So it's okay. But it's not okay all the time. On the opposite, of course, the heat is distributed on the beta phase. There are additional things. Once again, because of periodicity condition, there is a little influence of the Becquerel number, and of course you can calculate that for complex materials, take X-ray tomograph images. But you basically have always the same section. And let us take an example of application. I have a stagnant system, and then so homogeneous temperature, and then I introduce some heat at the interface, and basically I will have the following situation: the temperature of both faces at the macro scale will increase. There will be a transient evolution. Everything is transient, but if I look at the difference between the two macroscale temperature, then after a while, all the two temperature increase, but the difference remains a constant. And this difference can be predicted by the two equation model with this distribution coefficient. And actually, the math gives that following result. So you have a difference that depends, of course, on omega. If there is no omega, there's no difference. And it depends on the heat capacities of the system, and it depends on the distribution coefficient and the exchange term in the system. There is a competition here between the heat, that is exchange between the two systems. And you have the points here are TNS predictions, and the curves, the red and blue curves, are the predictions. So it works relatively well. And something interesting, you would think that the temperature is higher in the most conductive material. Looks, I think quite heat will go to the, well, not necessarily. There's an example here. If I look at the pore scale temperature, same Fermat conductivity ratio, but with different thickness of the phases. And the trick is there. I see here, for a given, I see here the average temperature, so the sigma is here. So I would expect that the higher temperature is in the beta phase. This is correct if the beta phase is relatively thin, and I have that here, so I have a trough here. But if I increase the thickness of the beta phase, then there is heat resistance in the beta phase, which overcomes the fact that it has a higher conductivity. So I may have both situations. Either the highest temperature is in the highest conductivity material, or it might be in the lowest conductivity material, depending on the relative thickness of the two things. So but you see that this is not a simple problem. It's quite involved, but you can understand all that with.
Excuse me, I missed what happened to the surface average of the source terms. Did you just rename it as omega?
Yeah, omega. Omega is the, yes, in this particular case, omega was the constant. Okay. That's the most straightforward answer. Otherwise, it would have the range so well, that's the same idea. The idea that the highest temperature might not be in the phase with the highest conductivity. Let us take an example. If I if omega comes from combustion, then there is a coupling between the heat transfer problem and the mass transport problem, and you can use upscaling and see that well it works relatively well, especially if you have a small dipolar number. So here you have predictions of the temperature in one of the phase, DNS and the black line of the prediction. If you have a large dipolar number, then the distribution of the heat tends to have a characteristic length which is small, and therefore an average model has always difficulty. But you see that there are some applications for that. And recently, for those people interested in transfer, radiative heat transfer in closed media, a local non-equilibrium model was developed using that distribution coefficient theory. So I refer to literature on that, but for people who are interested by non-equilibrium model with radiative heat transfer, then there are some solutions already available in the literature. Well, I believe that's the end. So I just wanted to give an illustration here of the this kind of analysis. So I did a lot of work on the behavior of ablative layers of rockets. So they are made of composite materials, either carbon-carbon or carbon resin. And this is a multi-scale, really a multi-scale problem for which you have small fibers and deposit here. And then you have, so you make wires, and in between the wires you put resin or carbon, and so forth, and in the end you get that final system. And you probably understand that. The life of an ablative layer in a rocket is how much? 1 minute? 2 minutes? So you have a change in temperature which is enormous, 2,000 degrees, over a relatively thin layer. And so local equilibrium modeling might not work. And if you have a process like that, you have, of course, the heat transfer, but you have the pyrolysis of the material, you have mechanical problems, so you want to understand that. So I'm just illustrating using one of the slides. So we work on that. There are many possibilities.
During ablation, you also lose material.
Sorry?
During ablation, you also lose material.
You may have mechanical ablation also. It depends on the temperature is very high, and therefore the materials are not brittle anymore. So there is more chemical ablation in most cases, at least for non-mechanical ablation for almost particular system. And so what's here? This is the temperature for the. So we have some active phase that will have some sort of pyrolysis mechanisms, and we have the carbon fibers that do not have any chemical reactions, and you see that. So I'm not authorized to give numbers, but remember that we have a 1-2 minute time duration. So at the beginning, there is a strong difference, so it's really non-equilibrium. And then after a while, let's say the half time of the entire process, then we revert to a local equilibrium situation. So, well, not a big deal. Well, let's look at the pressure rise in the system. Pressure rise in the system actually will depend on your the thermal model you use. If you have an equilibrium model, this is the discontinuous lines are the prediction of the pressure field in the system, and the continuous line is the prediction of the non-equilibrium model. And you see there is some difference. And here, so these are some dimensionless pressure. It's very important. And so the mechanical stress induced, you will calculate with your equilibrium model, might be very, very different from the one calculated if you assume a non-equilibrium model. So you see there are many applications and there are many impacts of such models in the system. And that concludes my lecture, which I hope